Hey guys, I'm Kevin, and today I'm going to be going over problem 2 from exam 3 of spring 2022 semester. And here we have a circuit with 4 transistors, and we are supposed to find some resistor values, some small signal values, and another resistor value. They tell us that ID1 is 0.2 milliamps. They tell us transistor M1 is 0.5 volts from the edge of saturation. They give us the threshold voltage, gamma, and K prime W over L. And they also tell us the capacitors are large, meaning we can treat them as an open circuit for DC analysis and short circuit for AC analysis. They want an input resistance of 250 kilo ohms. And they tell us R3 is 2 kilo ohms and RL, the load resistor, is 20 kilo ohms. So to get the problem started, I noted down all the values they gave us, and I redrew the circuit just so it's easy for me to work on it. And one thing to note is that just by them telling us that transistor M1 is 0.5 volts from the edge of saturation, we can already derive a simple relationship between the drain voltage and the gate voltage of transistor 1. And we can do this by realizing that when VDS equals VGS minus VTH, which is the overdrive voltage, that's when the transistor is at the edge of saturation. So when they say it's 0.5 volts away from the edge of saturation, what they're telling us is VDS is 0.5 volts more than VGS minus VTH. And that's what I noted down there. And just by expanding what VDS means, which is VD minus VS, and what VGS means, which is VGS minus VS, and realizing that VTH is 0.6 volts, we can already do some simple algebra to come to the fact that the drain voltage of transistor 1 is going to be 0.1 volts less than the gate voltage of transistor 1. Another thing to note is that since gate current for all MOSFETs is always 0, when we look through the input right here, we see that the only place for current to travel is through R1 and R2. And when we ground all voltage sources, which is what we do when we try to find the input resistance, we find that the input resistance is simply R1 and R2 in parallel. And we can write this relationship down here as well, and we will need this later. A good rule of thumb is that for each unknown, you need a relationship or an equation that's independently derived in order to get a definite single solution. So we have two unknowns, R1 and R2, and we already derived one equation relating them. Now, in order to find the second equation, we need to realize the purpose of R1 and R2, which is to bias transistor 1. So to find the second equation, we need to find what gate voltage does this transistor 1 need to be in order to satisfy the values that they gave us. In order to find VG1, let's try to look at the circuit and form some relationships. And we can already note that since capacitors are treated as open circuits in DC analysis, the current that goes through transistor M2 is the same current that goes through transistor M1, and that's the same current that goes through transistor M3. And since transistor M3 and M4 are current mirrors, we can also conclude that the same current that goes through M1, M2, and M3 must also go through M4. We can also note that since we know the current that flows through transistor 2, we know the current that flows through R3, meaning we can use that to find the voltage drop across R3. Using those two facts, we can figure out that the voltage at source 2, the voltage at the source of transistor 2 is just 10 minus the value of R3, which is 2, multiplied by ID. Now I'm going to write the equation for saturation current through transistor 2, which is 1/2 K prime W over L, VSG minus the absolute value of the threshold voltage squared equals ID. Now since K prime W over L is 10, the threshold voltage is 0.6, and VS is 9.6, and ID is 0.2, we can simplify this equation quite a bit, and this equation is actually simple enough that we don't even need a calculator. We just need to ensure that we take the correct root when taking the square root to ensure that VG is less than VS and the transistor is in saturation. Now, looking at the circuit, we can see that VG2, VD2, and VD1 all are on the same node, and thus they must have the same current. And thus we can establish that VG2, VD2, and VD1 must all be 8.8 volts. Now, if you recall earlier, we also established another relationship, which is VD1 is 0.1 less than VG1. Using that relationship and the fact that we just learned VD1 is 8.8 volts, we can establish that VG1 is 8.9 volts. Now we have two equations that relate R1 and R2, which is that R1 in parallel with R2, which is the input resistance, must equal 250 kiloohms, and the voltage divider that R1 and R2 form with the voltage source must give us 8.9 volts at the gate. I've written both of these relationships right here, and we can simplify the second relationship just a bit by dividing by 10 on both sides to give us R2 over R1 plus R2 equals 0.89. Now let's write out what it means for R1 and R2 to be in parallel. If you recall the equation for equivalent resistance for two resistors in parallel, you'll find that the equation for R1 and R2 in parallel is R1 times R2 over R1 plus R2. And we know that must equal 250. Now we can separate the left-hand side into two terms, which is R1 times R2 over R1 plus R2, and all of this still equals 250. Now if you also recall, we found that R2 over R1 plus R2 equals 0.89, giving us a simple relationship for R1, which we can solve. And we find that R1 is 280.9 kiloohms. After we find R1, we can simply substitute this value into the other equation to find R2. As a bonus, I quickly wanted to show how you would solve this in case you weren't allowed to ignore gamma, which we did when we solved it previously. I write down the equation for saturation current that incorporates gamma, and then I plug in all the necessary values, and then I get this cubic equation. And since a cubic equation is not as easy to evaluate by hand, I use a calculator to get three values for VG2. Since VS2 is 9.6 volts and the threshold voltage is 0.6 volts, we know that VG2 must be less than 9 volts. And only one of these values satisfies that condition, which is 8.81 volts. And we figure that VG2 and VD1 must equal 8.81 volts, and VG1 must equal 8.91 volts. We can find the resistor values with the same approach we used earlier. Now let's move on to part B, which asks us to find GM, R pi, and R naught. Now, one thing we figured out earlier is that ID is the same for all transistors, and ID is 0.2 milliamps. And we can use that to find GM for all transistors using this equation that relates ID and GM and K prime W over L. And we get, after evaluating it, we get GM equals 2 millisiemens. Now, R pi is infinite for all MOSFETs, as there is no current flow between the gate and the rest of the transistor. And R naught is related to ID using this simple equation, and after we plug in the fact that gamma is 0.12 and ID is 0.2, we find that R naught is 41.67 kiloohms. Now let's move on to part C, which asks us to draw a small signal model of this amplifier. Now, in order to draw a small signal model that we can analyze to get our necessary values, we need to make some observations that allow us to simplify the circuit greatly. And these observations are the fact that transistor 3 and 4 function as a current mirror, which I represented in this circuit right here, and transistor 2 acts as a controlled resistor, which I represented here as RM2. We can find the value of this resistor RM2 by using this formula that we derived in class. And in general, 1 over GM is very small compared to R naught, so we can make this approximation that says 1 over GM in parallel with R naught is about 1 over GM. And we can see that in our case, 1 over GM is 0.5 and R naught is 41.67. This approximation is valid because the accurate result, which is 0.494, is pretty close to the approximation, which is 0.5. After these simplifications, we can start to draw the small signal model. One thing to do when drawing the small signal model is to disable all DC sources, meaning anything that's plus 10 volts will now be represented as ground. Then, looking into the gate, we see that since both R1 and R2 go to ground, they must go in parallel to ground, which we've represented here. And since the current at the gate is always 0 for MOSFET transistors, we represent it with an open circuit right here. Looking into the source, we see that it's simply connected to ground, as capacitors are closed circuits in AC analysis. Looking into the drain, first we draw the voltage controlled current source, which is Gm multiplied by VGS, and since Gm is 2, we simply write 2 times VGS. And then R0 runs parallel to that voltage controlled current source, and I represent that here as well. After the voltage dependent current source and R0, we need to draw the load resistor, which carries current from this node all the way to ground. And we need to draw R3 and RM2, which in series carry current from that previously mentioned node all the way to the plus 10 voltage source, which we represent as ground in AC analysis. Now that we have our basic small signal model, in order to make concrete analysis a bit easier, I think it's important to clean it up a bit and connect all common nodes, which are shown here. The main simplification here is connecting all ground nodes together and also realizing that 2 times VGS is just 2 times Vin, because VGS is VG minus Vs, Vs is grounded so that Vs equals 0, and Vg is directly connected to Vn. From here it's pretty clear to see that what this current source is doing is drawing 2 times Vin current through these 3 resistors right here. And in order to find V out, we simply have to multiply the current, which is 2 times V in, by the equivalent resistance of these 3 resistors in parallel. However, while this gives us the gain for this particular configuration where the load resistance is 20 kiloohms, we're just trying to find the gain in the general case. Thus, we don't consider the load resistance in our calculations. The equivalent resistors of those 2 resistors in parallel is 2.36 kiloohms. Multiplying the current, which is 2 times Vin, by the resistance, which is 2.36 kiloohms, we get that the voltage drop across this resistor is 4.72 times Vin. And since this is a drop of voltage from 0 volts, we get that the voltage at V out is negative 4.72 times Vin. To find the output resistance, let's disable Vin, turning the whole thing into ground. And since Vin equals 0 volts, this current source also produces 0 current, turning this into an open switch. After this, it is clear to see that output resistance, which is the ratio of voltage at output to current at output, is simply this resistor right here, which is 2.36 kiloohms. Let's move on to part F, which asks us to find Rm, which is the resistor in the drain of transistor 4. Here I simplified the circuit by isolating it from everything else, and you can see here there's a node that goes on to connector M3, which I'm ignoring right now because all it does is provide the gate at M3 with a voltage source and no current flows through it, so isolating it is completely valid. Here I wrote down a relationship for VD in terms of ID and RM, which is VD, which is the voltage right here, is 10 minus the voltage drop across this resistor, which is equal to ID, which is 0.2, multiplied by the resistance. And since the drain and the gate are connected, VG also equals VD. Here I wrote down the equation for current through a transistor when it's in saturation, a MOSFET transistor that is, and the equation is 1/2 K prime W over L, VGS minus VT squared, equals ID, which in case is 0.2. Now VGS is just VG minus VS, and since VS is grounded, we can just write that as 0. And VT in this case is 0.6 volts, and after further simplification, this equation is pretty easy to solve by hand, as long as you take the correct route that leads to the transistor being in the active region. Since we just found out that VG is 0.8 volts, and then VG must also equal 10 minus 0.2 times Rm, we can set those two equations equal to each other and we can solve for Rm, which gives us Rm equals 46 kiloohms. Here I summarized all my answers in just one slide, just in case you wanted to solve the problem by yourself and you wanted just one number to quickly check your answer up against. And other than that, thanks for watching. I hope the examples were easy to follow along. Good luck on your finals.